So, as stated on Friday, 1.5 is all about solving different types of equations. The textbook sort of puts all the types in one. I thought that was way too much. So I'm chopping it up over the next several days. On Friday, we talked about linear equations. Today, we're going to talk about nonlinear equations, specifically quadratics. Now, I hope that the idea that we got from Friday's practice was that, well, even if you didn't do the advanced one, I hope you guys saw the advanced assignment, that no matter how big and ugly a problem is, when it comes to linear equations, they're basically always the same. So this is just a random example that you saw from Friday's practice. If you did the advanced one, I'm going to write it down, but we're not going to solve it. But, problems like, I don't know, 2x minus bracket 3 plus 2 parentheses 5x minus 4, close the parentheses. Let's toss in the minus 8x for fun. Let's close the bracket. Let's add a 4 to it. Equals, I don't know, 9 bracket negative 7 minus parentheses 8x plus 2, close the parentheses, close the bracket, minus 1, right? I know. The whole point of Friday's lesson, if you did the advanced one, was you got some really ugly linear equations. I think I gave you like 10 of them or something. Yeah. But, the hard ones. But if you followed my tips, simplify both sides, don't start solving the equation yet. All of those problems basically boil down to something like, and I'm making this up, 5x minus 3 equals 7. Like every single one of those hard problems, it started off complicated, but if you went through the tips, simplifying both sides first, you always ended up with a very simple equation like this. Because all you need are inverse, I guess I'll put a line here, operations to solve equations that only have one variable term, or if you have multiple variable terms, they're all at least the same type. Right? And that was sort of the idea I wanted you guys to get if you did the advanced assignment, that all these crazy complicated linear equations, because it's linear, that means all of the x terms were like terms. You could eventually simplify them by combining like terms to always get a very relatively easy. All right, I guess I hit another kid. Yes, I'm recording. Yes. I was just joking, future parents. Yeah. I don't think they can, fortunately, I don't think they can pick up you from that far away. What was I saying? Oh, yeah. Because linear equations, all the x terms are linear, you eventually can combine them. Now, notice this big idea. I didn't say linear equations. I just said equations in general that only have one type. So for nonlinear equations, quadratics, cubics, quartics, square root equations, that holds true as well. So let's take a look at this simple nonlinear equation. Say 45 equals 25 times x plus 7 squared minus 4. Yeah, it looks fancy because we have an exponent. But the important thing is, I only have one variable term. There's my variable, and he's a part of this term here. So because I only have one variable term, I don't need fancy methods. I don't need fancy techniques. I don't need formulas. Just use regular inverse operations to get that x by itself. So let's do it. Get rid of the thing farthest away first. So we're going to add 4 to both sides. That's 49 equals 25, x plus 7 squared. Now that the variable term is isolated, you want to go ahead and strip off the outer numbers, the outer parentheses, so on and so forth. So to strip off the 25, we divide out the 25. Again, we're just using inverse operations. And then to strip off the square, we use the inverse, which is a square root. Now, we've done square roots of fractions before. You just apply the square root separately to the numerator and denominator. So that is 7/5, 7 over 5. A little footnote here. When you take an even root, when I say even roots, I mean square roots, fourth roots, sixth roots, eighth roots, that sort of stuff. When you take an even root, but more specifically, to solve an equation, right? If you're just walking down the street and you're taking square roots for fun, you don't need to follow this rule, right? If it's Saturday night, you're having a party, and hey, let's just take a whole bunch of square roots. You don't need to care about this. But specifically, if you are doing a square root for the specific purpose of solving an equation, your results will be both the plus and the negative, right? So we actually need to slap on a plus or minus here. The reason being, when you're taking a square root for fun, hey, what's the square root of 25? It's just 5. What's the square root of 49? Oh, it's just 7. You're just getting a number. But when we're solving an equation, you're answering a question. What's x squared equals 4? And I have to use the square root to solve. You're answering the question, what number squared gives you a 4? That question has two answers, a positive 2 and a negative 2. So, long story short, if you're solving an equation and you take an even root, make sure you put the plus or minus. And then from this point on should be child's play, subtract 7 from both sides. When I have answers that have plus or minus mixed with regular numbers, I always like to put the plus or minus at the end. So this really isn't a math thing. This is more of a Mr. Vo trying to make math look pretty thing. So when I subtract this 7 over, I'm actually going to write the subtract 7 first, or negative 7, and then put the plus or minus at the end. Right. That's how I'd write the answer. Now, the next thing I'm going to talk about is a Mr. Vo thing. This is not a math thing. For me personally, if my final answer has a plus or minus in it, and it does not have special symbols, like square roots or i's or anything like that, I'm going to expect you to split apart the answer. In other words, I don't expect you to leave it like this because they're just regular numbers. I expect you to go ahead and write it out as negative 7 plus 7/5 and negative 7 minus 7/5, and go ahead and do the arithmetic to give me two separate answers. So again, please, if it has regular numbers, do not leave it like that. Go ahead and split it apart and figure it out. So that's what, negative 35 plus 7 is a negative 28, and a negative 35 minus 7 is a negative 42. Right. So those would be the two answers I would accept. Okie dokie? Okay. So that was an example of a quadratic equation. Hey, we solved it, and we didn't use anything special, just inverse operations, because they only had one variable term. Of course, now, logically, the question is, well, what if there are more than one variable terms that you cannot combine? Quadratics belong to a family called polynomials, and all of polynomials equations can be solved, mostly, utilizing one very, very important, probably the most important idea in the world of polynomial solving. And it's an idea that we probably learned in 5th grade or 4th grade, whenever you guys learned your timetables. It's called the zero product property. A 4th grade concept that is invaluable to higher mathematics. The zero product property states, if we're working with real numbers, obviously if you work in different number systems, this may not be true, but specifically for real numbers, which we will be working with, if you have a multiplication problem and it equals 0, then irrefutably, no arguments, it is law that at least one of those pieces must be 0. Then either A is 0 or B is 0. Why is this so important to solving polynomials, not necessarily just quadratics? Is because it allows you to break down problems into manageable pieces. And that's what makes polynomial equations hard. You're dealing with x cubes, x to a fourth, x to a fifth. Those are hard problems. Zero product property allows you to chop them up. But the important aspect of it, what does the zero product property require? It requires that your problem is a multiplication problem. In other words, it requires things to be factored. It also requires the equation to equal 0. Right. If your problem is not factored, if the equation does not equal 0, we cannot implement this idea. So let's take a look at an example here. Suppose I ask you to solve, I don't know, 7 minus 13x equals 3x minus 3. 3x squared. Yeah, make it look an actual quadratic. So I hope we can see that this does not follow the first idea that we talked about, because here we have two x terms, two variable terms, and they're different. They're not the same type. One's an x squared, one's a regular x. I can't merge them. So when you do not have an equation with just one variable type, your only option, set it equal to 0. Move everything onto one side. Doesn't matter which side we move things on. I like to keep the biggest exponent positive, and the biggest exponent is an x squared. So since it's on the right-hand side, I'm going to move everything to the right. That means we're going to subtract the 7 over and add the 13x over. Hopefully that gives us 0 equals 3x squared plus 13x minus 10. And to exploit this idea, all you have to do is factor. So I'm not going to spend a lot of time on this. I'm just going to fast forward through it, because ideally we should be a little bit better at factoring. If that's still a false statement, please practice. Please get caught up soon. Please ask me for help if you need it. So let's see if I can remember how to do this. What is this? 10 is 1 and 10, 2 and 5, 15 and 2. So it's a positive 5 on the right, minus 2 on the left. Okay. So the zero product property, hey, we have something factored, and he equals 0. So that means each individual factor can possibly equal 0. So what was once a quadratic equation is now broken down into two relatively simple linear equations, which we can then solve regularly. X equals 2/3, x equals -5. Okay. Easy peasy? Yep. So when it comes to solving quadratics, or any polynomials really, the name of the game is make sure it equals 0 and factor, factor, factor. In a perfect world, everything would be easily factorable, but of course not everything is easily factorable. So what if we have a polynomial, specifically quadratics, because that's the topic of this section. What if we have a quadratic that's not factorable? For non or not easily factorable, non-factorable quadratics, you basically only have two options. You can ... Number 1, complete the square, which in this class, because I'm super duper lazy, I will always abbreviate CTS. So in the future, if you see CTS, I usually mean complete the square. Or you can use the quadratic formula. I am not going to go all out with lessons on where the quadratic formula came from, how to use it. I'm going to assume by now, after going through Algebra 1 and Algebra 2, we've done the quadratic formula to death. I will, however, for the sake of completeness, write down the quadratic formula just in case you forgot what it was, but I'm not going to do an example. I'm not going to explain where it came from. Right. So the quadratic formula states this. For any equation of the format ax squared plus bx plus c equals 0, where a, b, and c are real numbers, the solutions x will equal opposite b plus or minus the square root of b squared minus 4ac all over 2a. Right. So if you're faced with a quadratic that you just can't factor, or it's too difficult looking, you always have this in your back pocket. This is like your ace in the hole. This is your, I've tried everything, my back's to the wall, I'm completely stuck. Quadratic formula will always work. It's lengthy, it's long, it'll take a long time in a lot of places to make a mistake, but if you do it correctly, it always works. Quite frankly, I much prefer completing the square. If a quadratic is not factorable, completing the square is probably the most favorite thing, for me at least, to do in the topics of quadratics. Because it's not a fancy formula. It's not a crazy complicated idea. All it is recognizing patterns. So what I want to do first is just sort of... Man, I'm just abusing kids today. All I want to do is just talk about where completing the square comes from briefly. I know some Algebra 1 and Algebra 2 teachers sort of brush it away. I have had like half of you last year, so you guys have heard the spiel, but for the rest of you, I don't know. So let's just cover our bets, talk about where completing the square comes from. It comes from the idea of squaring a binomial. If you take a binomial, say x plus 3, and you square it, there is a pattern. We talked about it when we did the multiplication lesson. It's x squared plus 6x plus 9. No, I didn't memorize what x plus 3 quantity squared is. I just followed the pattern. Let's just do a couple more, or a few more. X plus 4 squared, x squared plus 8x plus 16. It doesn't have to be plus. It works with minuses. X minus 5 squared is x squared minus 10x plus 25. And let's do one more just to even out. 2 pluses, 2 minuses. X minus 6 squared, x squared minus 12x plus 36. Okay. The reason why completing the square works is because on the left-hand side, just so we're talking about the same vocab, these are square of binomials. On the right-hand side, these are perfect square trinomials. So I'll be using those terminologies just so you know what I'm talking about. The reason why completing the square works is because the structure of perfect square trinomials has the same relationship to its square of a binomial. If you look at these patterns row by row, notice that the constant term in the binomial is always half of the middle term in the trinomial. The constant in the binomial is half of the middle term in the trinomial. Constant in the binomial, middle term, trinomial. Constant in the binomial, middle term in the binomial. It's always going to be that relationship, that 1/2 relationship. And if you look at the constant term in the trinomial, this, for example, in the first row, this 9, it's 3 squared. This 16, 4 squared. 25, 5 squared. 36, 6 squared. The last term, the constant term in the perfect square trinomial, is always a perfect square. We can sort of color code this. Our observations were that the yellow would always be 1/2 of this lighter color. I think it's blue. Right. Thank you for confirming that. First and third hour did not confirm that for me. And this color here, I think it's whatever. Orange, thank you. We said that it was just the yellow squared. So where does completing the square come from? It's just connecting these two relationships by the yellow. Yes.
If you don't complete the square, you can always do quadratic formula.
Yes, that is true, but completing the square takes 10 seconds. Quadratic formula takes a minute. What? Let's take a look at this color right here. Look, what's more to memorize? That orange is just yellow squared,
You're like, I remember yellow is.
but the yellow,
Just look at the number.
is nothing more than 1/2 of the blue squared. That's it. This is the only pattern that you need to know. That to complete the square, you just need to take half of the middle coefficient and square it. But yes, to answer your question, you can do everything with quadratic formula.
There's what are the rules for the x, like x squared?
Yeah, I'm gonna write down the rules. Yeah.
I'm like, that's what I want.
Now, why would anyone be turned off from completing the square? Because of this idea here. Yeah. Note, completing the square is easiest, right? I'm not saying it's impossible, but it's easiest when the following two bullet points are true. The leading coefficient, if I can spell, is 1. That is to say, the x squared term has a 1 in front of it. And the middle coefficient is even. And when I mean the middle coefficient, I mean the regular x term. So if I had a problem that wasn't factorable, and the leading coefficient is 1, and the middle term is even, completing the square is pretty easy to do, and I would do it. If any one of these is not true, well, I, Mr. Vo, personally would still do it, but I'm going to assume you guys would not want to do it. Then I would use quadratic formula. Do know I said easiest, not impossible, because if any of these or both of them are not true, completing the square will work. Completing the square will work for any problem. It's just if these bullet points are not true, you have to deal with fractions. You have to deal with like ugly radicals and rationalizing. So I would say this. Solving quadratics, assuming that you have more than one variable term. If you only have one variable term, you just go ahead and solve it directly. But solving quadratics, you're going to try to factor first. If factoring is not possible, completing the square, only if the above two bullet points are true. If any of those two above bullet points isn't true, use the quadratic formula. Now, if any of those two bullet points are not true and you still want to do completing the square, talk to me after the lesson and I will show you one-on-one. But I'm going to assume for the majority of us we don't want to see it, so we'll skip it. Did anyone want to see an example of completing the square in action? Alrighty. I did. Okay.
I don't know how to do that.
Sure. So let's do one example here. So completing the square example. Did you need something? You want to find what? Oh, the bottom right drawer. Yeah. Let's say I ask you to solve x squared plus 8x minus 5 equals 0. Right. It's a quadratic, two variable terms, so I need special methods. It already equals 0, so they did have to work for me. First thing I'm going to try is factoring, parentheses, parentheses. Oh no, this guy isn't factorable. Who would have thought? So leading coefficient is 1. Middle term is even, so completing the square might be easiest here. To complete the square, the reason why this guy wasn't factorable is because this negative 5 here. This negative 5 will not work with this problem. He's useless to us. And what do we do with useless things? Get rid of it. Math is a terrible world. It's a cruel world. We get rid of useless things. So I added 5 to both sides. Now I'm going to follow that very simple and not complicated at all pattern. It's just half the middle number squared. So half of 8 and then square it. That's 16. Right. So I'm going to put a plus 16 here. But of course, this is an equation. What you do to one side, you do to the other side. Now the reason why we did plus 16, we complete the square, is that this guy's now a perfect square trinomial. He's factorable. But here's the cool thing. You don't even have to do any thinking because it always factorizes in the same pattern. Whatever this letter is, in this case it's x, whatever this symbol is, which in this case is plus, always half this number, parentheses squared. When you do completing the square, that is always the factoring problem, a pattern. Letter, same symbol, half the number, parentheses squared. And that now notice it's a one-term equation. Solve it using inverse operations. Square root both sides. Subtract the 4. My answer has a plus or minus, but it has a special symbol, it has a radical. So I'll just go ahead and leave my answer like that. If you were doing this on your own without explaining notes or making a video, that would have taken you like 10 seconds. Quadratic formula, g, negative 8 plus, or I don't even bother trying because it's going to take too long. Right? Yeah. I don't hate the quadratic formula. I just don't want to. It's like going fishing with a grenade. I'd rather use a rod and reel instead of blowing up the lake. You get the fish in the end, but one way's better. Right. The last tip, the last suggestion I have for you, so this is the end of the notes. Be aware of quadratic patterns. Right? Quadratics in the world of polynomials are probably, with the exception of linear functions, are probably the easiest types to solve. I'd rather solve a quadratic versus, I say, a cubic, quartic, quintic. Bless you. So if I had a big problem, say I gave you an x to the 10th problem to solve, that would be nerve-wracking. But if I could somehow spot quadratic patterns, I can use that to my advantage. Now, what is the quadratic pattern? What is the quadratic form? Let's just write down several random quadratics. So no rhyme or reasons. I'm just throwing random numbers up here. Say 2x squared minus 5x plus 3, 8x squared plus 6x minus 1, 3x squared minus 7x plus 5. Right. I just wrote down some 3 random trinomials, but they all share some similar characteristics, some similar structures. First of all, notice all ends in a constant. So quadratic trinomials will always end with a regular number. Because it's a trinomial, we always will have 3 terms. And notice in all of these quadratic trinomials, the middle exponent is a 1, whereas the degree or the leading exponent is a 2. And the relationship between 1 and 2 2 is twice as much as 1. 1 is 1/2 as much as 2. So the middle exponent is 1/2 the degree. So although quadratic trinomials are very easy to spot, it's always x squared plus x plus a constant. If you recognize your equation has this structure, 3 terms, the last one's a regular number, and the middle exponent is exactly half as much as the big exponent, you can treat it like a quadratic. For example, suppose I ask you to solve x to the 4th minus 9x squared plus 20 equals 0. At first blush, it's like, oh my goodness, Mr. Vo, you haven't taught us this yet. We're talking about quadratics, and all of a sudden you gave us an x to the 4th. Yes, this is something I haven't taught you guys yet. However, notice, we have 3 pieces. The last piece is a regular number. The middle exponent is exactly half as the biggest exponent. It's not a quadratic equation, but it behaves like a quadratic equation, which means we can solve it as if it was a quadratic equation, as long as we do a variable substitution. Use whatever variable you want Typically in higher math, we use the letter U. So what do we let the letter U be? I always let the letter U be whatever is the middle variable term. So the middle variable is x squared. So I'm going to let U equals x squared. How does that help us? Well, recall that x to the fourth is just x squared squared. So it's just u squared. So I can rewrite this problem as u squared minus 9u plus 20 equals 0. Now, what was once a difficult problem, a quartic equation, is now a relatively simple quadratic equation. Solve it by factoring, solve it by completing the squares, solve it by quadratic formula. All those methods will work with this guy. Fortunately, I picked an example that was factorable. U and u, minus 4 minus 5. So u equals 4, u equals 5. Those are our answers for u. Unfortunately, I don't want u. I don't like u. I want x's because that was the original problem. So all you got to do is back substitute the what the u was. So u was x squared. X squared equals 5. And then square root both sides. You're done. Go home. Be happy. X equals plus or minus 2. X equals plus or minus root 5. Right. So noticing quadratic structures can help you save a lot of headache if you recognize that your equation or the problem that you're solving for has that sort of behavior. I'm going to write down this example, but we're not going to solve it because I think you get the idea. Suppose you had like 2 minus 5x squared plus 7 times 2 minus 5x plus 12 equals 0. Normally, that would require you to expand everything out, distribute the 7, go ahead and apply the exponent of 2. But if you notice, you have 3 terms. The last guy is a constant. And this parentheses has an exponent of 1. This parentheses is an exponent of 2. So I could expand it, or I could let u be what? 2 minus 5x, and then you just go ahead and solve it like a regular quadratic. I'll let that be an exercise for you. Haha, for you. But that's it. That's how some tips and techniques of solving quadratics.
I thought you were talking about someone